Hello, welcome to this video. This is a video about identity operator in coherent state basis. So just let's recall what's the context in which we're developing this framework on, and we can keep focus on this context, and it's the following. We want to develop a theory that is classical in order to do what? To calculate traces, and in a much more specific form, partition functions using a classical field as the basis state of our representation. So then this is kind of the main task. So we want to calculate traces or partition functions where the state in which we're representing our quantum mechanical system is the most classical state that we can possibly find. So then, in that order of ideas, what's the most classical state we can find? Well, it's the coherent state. So, as for light, or for harmonic oscillators, coherent states are the most classical states. And what does that mean? So that means that for a coherent state n, the term sigma x sigma p, which is the multiplication of the uncertainties in momentum and position, hits exactly the boundary of the uncertainty principle. That's what a coherent state means. It's a state for which this identity complies. So now we will see some review of how to calculate the partition function in just a plain quantum mechanical state, let's say Fock state, and then we will do the following. So if we are in a normal quantum mechanical state, the ones that we're used to calculate stuff in, we say that the trace of A is equal to the summation over n of the expectation value between n, a, and n. So this is just the summation of the diagonal elements of operator A. This is possible to be done in this way because there exists a unity operator such that the summation over n of n is equal to 1. So this is important. Now, following the same order of ideas, if we want to represent a partition function in coherent state basis, let's say we want to write z equals to the trace of e to the minus beta h coherent state basis. So what we have to do is to find a way to compute z equals to the summation over n of n, the expectation value of e to the minus beta h, and where this n is a coherent state for our particular representation. Coherent state. And so the question is, how do we do this? We have to choose a proper state to actually represent this this trace. Just recall that z is equal to the trace of e to the minus beta h. This is equal to the summation over n of n e to the minus beta hn. So in this order of idea, so what is the most classical state that we can choose to calculate this partition function on that specific representation? So that will be the coherent state. And a coherent state is by definition an eigenstate of the destruction operator. So that means that we have that if phi is a coherent state, then it follows that a operator on phi is equal to an eigenvalue a. So an eigenvalue, well, we will denote it here as phi times phi times state. And let's rewrite this like this. So this is the definition of coherent state. And as for just when we do the calculation with plain quantum mechanical states, we need the existence of an identity operator. If we do it in coherent states, we need an existence of an identity operator in coherent states too. So identity operator in coherent state basis. So the big question is, what is it? And that's what concerns us in this video. We will not talk so much about calculating partition functions yet. We will just mention that for such a task it's important to have an identity resolution operator in coherent state basis, and that's what we're going to do now. So let's start like this. In plain quantum mechanical basis, Fock states or whatever state that you want to choose, you have the identity resolution that the summation of all the diagonal elements of the density matrix is equal to 1. This is the identity resolution. Is a very powerful mathematical trick to solve a bunch of nasty problems. So for instance, to calculate linear response coefficients, just to evaluate complicated commutation relations, to evaluate really complicated expectation values. So this is really useful, and what we want to do now is to see what will be the form that this takes in coherent state representation. So we will start with this ansatz, and we will say that there are some classical fields, 5 star and phi, which we will choose as our basis, and we will call them coherent states. And then the integral of d phi star d phi divided by 2 pi I times e to the minus phi star phi times the ket of phi times the bra of phi is equal to 1. So we want to know if this is truth or not. if we can comply with this resolution identity. So for such a task, we will do the following. So we will start by defining what are these ones. What is this? So then let's do the following. The coherent state 5, it can be expanded as the summation over m of some eigenvalue 5 of this, which is an eigenvalue of the coherent state, which as such is an eigenstate of the destruction operator, as we just saw just a little bit earlier, that the definition of a coherent state complies with this expression. This is the destruction operator or annihilation operator, and this is the eigenvalue of that coherent state. So then we can expand the coherent state as a summation of phi, which is the eigenvalue to the power of m, divided by square root of m factorial times m. See, so then now we will see that this coherent state has an amplitude and a phase. So then we can write phi as rho e to the I theta. And that means that the coherent state phi is equal to the summation over m of rho e to the I theta to power of m times the state m, all divided by square root of m factorial. Okay, so if we simplify it a little bit, we can just say that this coherent state is the summation over m of rho to the power of m e to the power of I m phi n theta, divided by square root of m times the state m. Now, important question. What is, this is the ket, and what's the bra? This thing here is the ket. Ket coherent state, let's do the bra. So the bra is just the complex conjugate. We'll use a different summation index n, and it will be phi star. Phi star to the power of n divided by square root of n factorial times the bra n, and this just let's recall the definition of the coherent state. So if we recall that definition, so we will see that the coherent state is an eigenstate of the destruction or annihilation operator. Therefore, if I just take the complex conjugate of this expression, I will get this, that the bra coherent state is an eigenstate of the creation operator, whose eigenvalue is phi star, and this way. So then, if we recall this, then we can identify this phi star as the eigenvalue of a creation operator applied on a bra coherent state. So then, following the same logic, we can just recall that the coherent state has a phase and an amplitude or a magnitude e to the I theta. So that means that phi star is equal to rho, this is real, times e to the minus I theta. Then the bra coherent state is equal to the summation over n times summation over n of rho, not times, of rho to the minus I theta to the power of n times the bra state n divided by n factorial, square root of n factorial, and then we finally can compute what is phi ket and phi bro, like this. So this type of density matrix term, so this is the summation over m rho to the power of m. Okay, this is left this without simplification, so this is rho to the n e to the minus I n theta, bra of n divided by square root of n factorial. We have to just plug that in here, so just so you know how we're going to plug it in. So this is rho to the power of m. Let's write it clearer. E to the power of I m theta square root of m factorial times the ket of m summation over n rho to the power of n e to the power of minus I n theta. Then this is the bra of n, and this is divided by the square root of n factorial. If I further simplify this, I take the summation out. This is m comma n, summation indices. This is rho m plus n. This is e to the I m minus n theta divided by square root of m factorial. And this is m ket times n bra. Now we have something here. It looks good, apparently. But what we have to prove furthermore is that this integral serves for the means of a unity operator. So I have to prove this. So what I'm basically doing here is that I'm in this expansion of coherent states is that I'm expanding coherent states in any other quantum mechanical basis. See? So then remembering that the coherent state, as we said, has a phase and a magnitude like this, I theta. So then we can replace that this ansatz in here in this formula, and we can write it like this. So first of all, we can say that the phi star d phi is equal to rho. This is equal to rho. No, just a minute. I think I should do something before moving forward. We should express this differential, d psi star d phi, in terms of something that depends on d rho d theta. This is an important step. I will not go through the details of this, but I can try to just post a video about the Jacobian transformations, just in case you're not very well acquainted with this, that sense, but I will tell you this. If I perform a coordinate transformation, the relationship between the volume elements can be cast in terms of the Jacobian of the transformation. Okay, so then we're going to do this. I wasn't planning to do so much algebra in this, but I think it's just important so you know how can we actually transform this ansatz for the identity operator into something only in terms of rho and theta, and then after the integral, how this will actually come to be one. So that's the main focus, the main task that we have to solve in this video. And so I think it's just good if we go through the Jacobian of this transformation from phi star phi to rho and theta. So let's write this. Phi is equal to rho times e to the I theta. That means that the phi is equal to the rho e to the I theta plus I rho e to the I theta d theta. Now phi star conversely is equal to e to the minus I theta. That means that the phi star is equal to the rho e to the minus I theta minus I rho e to the minus I theta d theta. Now, using these expressions for the phi and the phi star, we can do something, and we can write this in matrix form. So we will do it like this. So we'll write the phi star, and here we will write the rho d theta. Now then, what are the matrix elements that define this transformation? So the matrix elements that define this transformation, I will write them in green, but just 1 minute. So this, everything that multiplies the rho, so that means this term here and this term here shall go in the first column. So then we have here e to the I theta, e to the minus I theta. Now, everything that multiplies d theta, this one here, so this term and this term shall go in the second row. So then I have I rho e to the I theta, and I have minus I rho e to the minus I theta. This matrix defines the transformation from phi star to rho theta. Now, we want to know what's the Jacobian of this transformation. The Jacobian of this transformation, theta rho, is equal to the determinant of ei theta, I rho e to the I theta, e to the minus I theta, and minus I rho e to the minus I theta. This determinant is this. If I multiply this two, the exponentials just cancel each other, and I get minus I rho. Then minus this cross multiplication here, minus I theta and I theta go with each other, and then I get again minus I rho, and then I get 2 minus 2 I rho. See? Now I can write this. The volume element, that's right, or the volume or the phase space element, or yeah, whatever you want to call that. I don't know what notation do you use for that. So because some people say, yeah, but it's not a volume element. Well, it is in the coherent state representation, or in the coherent state plane. So then this volume element is equal to the absolute value of the Jacobian of the transformation. Just 1 minute, screwed up here. So times the rho d theta. That means that d phi star d phi is equal to the absolute value of this thing here, which is 2 I rho d theta. Now there is something here that we can as well do, which is the following. Where is the calculation here? And is this. What we're interested in from this integral that we want to assume that is the unity operator in coherent state basis, 2 pi I e to the minus phi star phi equal to 1, is it? So then we want to know we don't want to know what's d phi star d phi, but we want to know what's d phi star d phi divided by 2 pi I. So then if I divide both of these sides above by 2 pi I, then I will get that actually d phi star d phi over 2 pi I is equal to 1 over pi rho d theta. So then I can write this integral in the following way. Integral of d psi star d psi divided by 2 pi I e to the minus phi star phi this ket phi bro phi. This is equal to the integral rho goes from 0 to plus infinity, and theta goes from 0 to 2 pi. So then that means that I have two integrals from 0 to plus infinity, from 0 to 2 pi. This thing here is written as rho d theta divided by pi. This e to the minus psi star, which is rho e to the minus I theta, times rho e to the I theta, times what we found earlier for this product, ket phi bro phi. What did we find for this? So let's check. We said there is this term here. So we said it's this term here. So we can just move that term downstairs. Summation of mn of rho of m plus n divided by n factorial e to the I m minus n theta, and this is m n. So then we can compute this integral. We can continue in the computation of this integral, and we will do the following. So these two exponentials go away. So then what we have is integral from 0 to plus infinity, 1 over pi rho d rho. We have rho d rho here. We have e to the minus rho square, because it only remains this rho times this rho. We have the summation over m and n, rho of m plus n divided by n factorial, and we have here the integral from 0 to 2 pi of e to the I m minus n theta, the theta everything times ket m bra n. We can continue with the simplification in the following way. So what we're going to do is that we're going to pull the summation outside like this. We're going to multiply and divide by 2 to write this in the following form. To write 1 over square root of n factorial integral from 0 to plus infinity. Let's move this here just for a little bit, of 2 rho d rho e to the minus rho square actually times rho of m plus n. And let me see what am I missing. The pi, I multiply above by 2, so I have over 2 pi. So then this is times the integral of 0 to 2 pi e to the I m minus n theta divided by 2 pi d theta. So what do I have here? I have the summation over m and n, 1 over square root of n factorial. I have, let's write this in this way. Let's write this integral from 0 to infinity to rho to the m plus n e to the minus rho square d rho. Oh, here I forgot to multiply by the ket m Brian. Here then I say the following. Let me get this right here. So this is times the integral from 0 to 2 pi of e to the I m minus n theta divided by 2 pi d theta m n. Now just let's do this here quickly, like in just bloody blue. So this integral from 0 to 2 pi, it's nothing but this. This is this thing divided by I m minus n. And this thing here is evaluated between 0 and 2 pi. So actually, if we just rewrite this down after performing the integral, you can see that the actual value of this integral is e to the I m minus n times 2 pi, which is the first when we replace the upper limit, and when we replace the lower limit is 1, divided by 2 pi I m minus n. So times this kind of cross product between, or not cross product, because cross product comes from vector product, but this mixed product of states m and n. So then this is equal to the summation of mn 1 over square root of m factorial n factorial 0 to infinity to rho to the power of m plus n e to the minus rho square d rho times, what I'm going to do is this. I'm going to factorize e to the power of, let's do this slow for some of you be able to track this calculation. So I'm going to do this. I'm going to write this first one as e to the I m minus n pi times e to the I m minus n pi. You can see that this thing is actually e to the I m minus n 2 pi. So then, I mean, that's just adding indices of when you multiply exponential. So then minus, we have a minus 1 here. So I'm going to do is that I'm going to write this down, e to the I m minus n pi times e to the minus I m n pi. No, it doesn't show up, but I mean, you can figure it out. All of this divided by 2 pi I m minus n. times get m bro n. So you can see that in this, just math, like actually really lame mathematical trick, but I just want to make sure that all of you are kind of able to follow. So here I can factorize this one and I can factorize this one. See? So I will write this. Let's write this. I haven't used black for a while. I'm the freak of colors. I like to change colors all the way through. That's actually how I learned physics too. I learned physics by labeling different stuff with different colors. So my lectures are really colorful lectures, but I hope you don't mind, but it's rather an advantage for you. So then this is mn 1 over square root of m factorial n factorial. This is integral from 0 to plus infinity of 2 rho to the power of m plus n e to the minus rho squared d rho. And we have the following here. Just a minute. Then times, I just factorized the one in yellow, m minus n pi. That means that this is e to the im minus n pi minus e to the minus im minus n pi. All of this divided by first 2I here, and then in brackets I will write down this other term, which is pi and m minus n. So then this is m minus n pi. What am I missing? I'm missing times get m bro n. This is equal to summation of mn 1 over square root of n factorial n factorial, integral from 0 to infinity of 2 rho to the power of m plus n e to the minus rho squared d rho. Now note this thing here. Now let's use orange. Yeah, used to be one of my favorite colors. This thing that I'm just boxing out or isolating in orange, that thing you can recognize. What's that? That's e to the I to the power of something minus e to the minus I to the power of something divided by 2i. That's the sign of that something. So then this thing here is just the sign of m minus n pi. That's what that is. So then we can proceed with the simplification of our problem. So this is times, this is times e to the I m minus n pi times sine of m minus n pi then we have here times get m bro n. Now let's do just a little analysis on this term. If m and n are integers, any couple of m and n will make the sign equal to 0. It doesn't matter. It doesn't actually matter how you choose m and m. You can have this the subtraction of two integers is an integer. So you can choose M&M however you want, and this will always be an integer of pi. A positive or negative integer of pi, it doesn't matter. But the sign of any integer of pi is equal to 0. So in principle, they should vanish, but it actually doesn't vanish, but only in one case. This only doesn't vanish when m is equal to n. Because even though sine of 0 is 0, we will have a division of 0 divided by 0, and one can show that this converges to 1. So actually only when m is equal to n, this is non-zero and is equal to 1. So then we can say that this is a delta of mn. And we can write summation over mn, 1 over square root of n factorial, integral from 0 to infinity, 2 rho to the power of m plus n, e to the minus rho squared d rho, let's see, times e to the I m minus n pi times delta of mn, ket m brought n. Now if we implement this delta on the summation, we are left with just the summation over one of the indices. This is m factorial, 0 plus infinity of 2 rho. Look at this, rho of m plus n, when they are the same, this is just rho to the power of 2m, e to the minus rho square, d rho. When these ones are the same, m and n, this is 1. And then times m ket m bra. Well, it looks like we're almost done. So, and it looks like this is equal to 1, doesn't it? Just think about the gamma function. What's gamma of x? Just think about it. So don't take it too seriously though. So now we will perform the following substitution to solve this integral. We'll say that x is equal to rho squared. That means that dx is equal to 2 rho d rho. Well, guess what? We have here 2 rho d rho in purple. So we can easily rewrite this integral as a function of x in the following way. So this integral, the one we were calculated, is equal to summation over m, or this integral, no, yeah, the complete integral, I mean. So the complete result. 1 over m factorial, integral from 0 to plus infinity, 2 rho d rho is equal to x, rho to the, dx, rho to the power of 2m is equal to x to the power of m. There we have, because x equal to rho squares, so if we exponentiate both sides to the power of, we get x to the m, and e to the minus rho square is e to the minus x, this times ket m brought m. This is equal to the summation of m. This is equal to the summation of m, 1 over m factorial. Let's write this integral in the box to not confuse with the other stuff written there. X to the power of m, e to the minus x, dx, ket m brought m. What is this? Well, that's just m factorial, isn't it? And what's m factorial? M factorial, it's nothing but gamma of n plus 1. And that's what that is. That is gamma of n plus 1. So then we can write this integral in the following way. Summation over m of 1 over n factorial times m factorial get m bro m. This go away. We're left with the summation over m get m bro m. And this is the identity resolution for any just quantum mechanical state M, which is the state in which we have expanded our coherent state basis. Now, having said this, we're pretty much done with this video. I will say this. Let's first write the result. With this, we have proved that the integral of the psi star, sorry, d phi star d phi divided by 2 pi I e to the minus psi star psi sine of phi ket 5 bra phi is equal to 1. So we have our resolution identity in coherent state basis, which was what we were looking for. So this is the main result of the video. So that's one thing. The other thing is this. Let's recall this couple of things. Coherent state. It's a coherent state, eigenstate of what? Eigenstate of the annihilation operator. So it goes like this. Or like this. This is an important relation. This is the definition of our basis. You have to know what's our base, what to understand our basis, what to understand the unity operator of our base. We have to understand the orthogonality of our bases. We have to understand the completeness relation, which is the same thing as we have here. This is as well called completeness relation. So we actually have to understand the representation of the bases that we have chosen to work out our specific problem, which in this case is the calculation of the trace. So as the trace for normal quantum mechanical states of, let's say, Z equal to trace of e to the minus beta h, as this trace was written in this way. Of course, in coherent state basis, we can write Z equal to trace of e to the minus beta h equal to the phi star the phi 2 pi I e to the minus phi star phi. This is phi here, this is e to the minus beta h here, this is phi here. So you can write something like this. So the thing is that how to solve this. So if we have this, how do we calculate the partition function of things? This is the big question. And when we have, if we can come up with a theory in terms of coherent state basis for these classical fields phi, in which we can kind of easily calculate the partition function, we have a field theory. For statistical mechanics. How cool would that be? So, field theory for statistical mechanics in which I can calculate z as something. I will not tell you just yet what, but we calculate something that just requires functional integration over classical fields. This is what I'm after. This is what we're after, and then we will actually know. I mean, the titles of the lectures will tell you. So, I mean, you don't have to be Donald Trump to actually just guess the what's the actual thing that we're doing with the partition function. You just see the title of the lectures, you will see that what we're trying to do is to calculate quantum mechanical observables for statistical mechanical observables for a statistical M samples using the coherent state path integral. So I recommend you to watch my review on just Feynman path integrals to actually just see where the idea of actually calculating transitions of the form n e to the minus beta h n as path integrals came from. I will give you a clue. This came from Kubo. So then, yeah, when you actually see this, we will then get into something that is called imaginary time formalism. But for that, we have to construct the path integral to evaluate the partition function. So we're not there yet, but the next partition function as a coherent state path integral for Bosonic classical fields. Careful, because for fermions there is a whole other deal. Well, not other deal, but we have to construct quasi-classical states for fermions. That is, fermionic coherent states. That's not so straightforward, but you can just take a look at it. And then we will come back. Just take a look at these things. I just want to give you a picture of how I will be evolving in the videos, and I hope that now you are convinced that in the coherent state representation we have also a completeness relation or an identity operator. So then now, until next time, and thank you for watching.